Welcome back, dear explorer. Pull your blanket a little closer tonight. Set down whatever is weighing on your mind. Let the day dissolve, just for a little while, and come with me. This is the Midnight Explorer. And tonight we are going somewhere extraordinary. Not a distant country. Not a lost civilization buried beneath sand and time. No, tonight, we are going somewhere far more intimate than that. Tonight, we are going somewhere that has always been with you. Somewhere that is, in the most literal sense possible, inside you right now, as you sit or lie here in this quiet moment. Tonight, we are going to talk about the secret language of life itself. We are going to talk about organic chemistry. Now, wait. Don't let those two words frighten you. Don't let the memory of a difficult classroom or a confusing textbook creep in and steal this moment from you. Because tonight, we are not going to talk about organic chemistry the way it was perhaps taught to you. We are not going to sit beneath fluorescent lights with equations swimming across a whiteboard. We are not going to feel the anxiety of an exam approaching like a storm on the horizon. No. Tonight, we are going to feel organic chemistry. We are going to smell it, and taste it, and see it the way the great scientists who discovered it first saw it, with wonder. With disbelief. With the kind of awe that makes a person sit back in their chair in a candlelit laboratory and whisper to the empty room around them, "How is this possible?" Because that is exactly what happened. That is exactly the emotional truth at the heart of this story. The greatest scientists who ever unlocked the secrets of organic chemistry did not begin their journeys with confidence. They began with confusion. They began with failure. They began, many of them, in the middle of the night, sleepless and restless, haunted by questions that refused to be quiet. And slowly, over centuries, they began to hear answers. So let me take you back. Let me take you all the way back to the very beginning of this story. To a time before laboratories, before periodic tables, before any of the vocabulary we now use to describe the invisible architecture of life. Let me take you to a world where the things we now call organic molecules were simply mystery. Where fire was magic, and bread rising in the morning was a miracle, and the sweetness of fruit was a gift from something divine. Let me take you there now. Close your eyes for a moment, or let them rest softly on whatever is in front of you, and imagine the world 10,000 years ago. Imagine the smell of it first. That is always the best place to start with any story about chemistry, because chemistry, more than almost any other science, lives in the nose. It lives in the breath. It lives in the sensory experience of being alive. So, imagine the smell of wood smoke curling up into a night sky filled with more stars than you have ever seen in your modern life. Because there are no city lights here. There is no electric glow on the horizon. There is only darkness, vast and deep and honest, and above it all, stars. Millions of them. Billions of them. The entire galaxy spread across the sky like spilled salt on a black cloth. And below that sky, there is a fire. And around that fire, there are people. They are not so different from you, these people. They feel cold and seek warmth. They feel hunger and seek food. They feel loneliness and seek the closeness of others. And they feel curiosity. That ancient, restless, ungovernable curiosity that is perhaps the defining feature of the human animal. They have gathered around this fire because fire is the first chemistry that human beings ever learned to control. Think about what fire does for a moment. Really think about it with fresh eyes, the way these ancient people must have thought about it. Fire takes wood, solid, cool, quiet wood, and it transforms it into something else entirely. It produces heat and light. It produces a kind of dancing, living energy that seems almost alive. And it produces, rising up into that dark sky, the sweet and acrid smell of smoke. What is happening in that transformation? What is the wood becoming? The ancient people around that fire did not have words for it yet. They did not know about carbon atoms or combustion reactions or carbon dioxide molecules escaping into the atmosphere. But they knew, in the deepest and most practical sense, that something profound was happening. That matter was changing its form. That there was a secret in the fire that they could use but could not fully understand. And that is, in a way, the very first chapter of the story of organic chemistry. Because what is burning in that fire? Wood. And what is wood? It is, in the language we are slowly going to learn together tonight, an organic material. It is made, at its most fundamental level, of carbon atoms linked together in long, complex chains and rings, linked to hydrogen atoms, linked to oxygen atoms, all of them arranged in elaborate molecular architectures that hold the wood together, give it its weight and texture and smell. When fire touches wood, it breaks those molecular bonds. It releases the energy stored within them. It converts the solid structure of cellulose and lignin, those beautiful, complex organic molecules, into carbon dioxide and water vapor and a small residue of ash. It is, though no one around that ancient fire could have said so, a chemical reaction of extraordinary elegance. And in that elegance, in that transformation, lies the seed of everything we are going to explore tonight. Now, stay with me beside this ancient fire for a little while longer, because there is something else happening here that is equally important. Someone. Let us imagine her as a woman with clever hands and watchful eyes, the kind of person who notices things that others miss. Someone has placed a piece of bread dough near the edge of the fire. Not directly in the flames. Just near enough to feel the warmth. And something extraordinary is beginning to happen to that dough. It is rising. Very slowly, almost imperceptibly at first, the dough is swelling. It is expanding. It is becoming lighter, airier, as if something inside it is breathing. And when this woman picks it up and turns it in her hands, she can feel that it has changed. It has a different texture. A different smell, something yeasty and alive and warm. What is happening inside that bread dough? Well, what is happening is this: tiny living organisms, so small as to be invisible to the human eye, are eating the sugars in the flour and releasing carbon dioxide gas as they do so. Those gas bubbles are getting trapped in the stretchy network of gluten proteins in the dough, and they are causing it to rise, to puff, to become the light and airy thing we call leavened bread. In the language of what we are learning tonight, this is organic chemistry happening in real time. The sugars being consumed are organic molecules. The carbon dioxide being released is a product of organic metabolism. The gluten proteins are organic polymers. Even the yeast organisms themselves are entirely built from organic molecules, proteins, lipids, nucleic acids, carbohydrates, all of them woven together in the impossibly complex tapestry of biological life. And this woman, this clever and watchful woman beside her fire, does not know any of this. Not in those terms. But she knows something that is equally important. She knows it works. She knows that if she keeps the dough warm and gives it time, it will rise. She knows that when she bakes it, the bread will be lighter and more delicious than flat bread baked without this process. She knows, in the practical and empirical way that all early humans knew things, that there is a reliable magic in this transformation. And she will pass that knowledge on. She will show her daughter, who will show her daughter, who will show her daughter, and on across 10,000 years, across an unbroken chain of human hands and human kitchens and human wisdom passed from one generation to the next, until finally, one day, a scientist in a laboratory in the 19th century will look at what is happening inside bread dough and will begin to ask not just what is happening, but why. And that question, why, is the question that opens the door to organic chemistry. But we are getting ahead of ourselves. The night is long and gentle, and there is no need to hurry. Let us stay with the ancient world a little longer. Because there is so much beauty here, in the things that people knew and made and used long before they had the language to explain them. Let us travel now, still in this ancient world, still in this time before formal science, through a marketplace. Imagine it. A marketplace in an ancient city. Perhaps Alexandria, perhaps Babylon, perhaps the great trading cities of ancient India or China. It does not matter exactly where. What matters is the feeling of it. The narrow streets are packed with people and animals and noise. The sun overhead is fierce and white, casting sharp shadows. And everywhere, there is smell. The sharp, almost electric smell of black pepper grinding between stone mortars. The warm, woody sweetness of cinnamon sticks piled in great heaps, their papery brown bark curling gently at the edges. The deep, resinous, slightly medicinal smell of frankincense, small golden tears of hardened tree sap that, when burned, release a smoke so rich and complex and ancient feeling that it has been used in religious ceremonies for thousands of years across dozens of cultures. There is turmeric here, vivid, almost aggressively yellow, staining everything it touches. There is indigo, in solid blocks of a blue so deep and saturated it seems to vibrate. There is henna, dried and powdered, waiting to be mixed with water and drawn in delicate patterns on skin. There is opium, kept carefully away from the general market, used by physicians for the only reliable pain relief available in this ancient world. Every single one of these substances, every spice, every dye, every medicine, every fragrance, is an organic compound. Every single one of them is built from chains and rings of carbon atoms bonded to hydrogen and oxygen and nitrogen and sulfur, arranged by the slow wisdom of evolution and plant biology into molecules of extraordinary complexity and specificity. The compound that gives black pepper its heat is called piperine. The compound that gives cinnamon its distinctive sweet warmth is called cinnamaldehyde. The compound that makes frankincense smell the way it does is a complex mixture of terpenes and sesquiterpenes, ancient molecular structures that plants developed over millions of years as signaling chemicals, as defenses against insects and bacteria, as attractants for pollinators. Turmeric's vivid yellow comes from a compound called curcumin. Indigo's extraordinary blue comes from a molecule called, indigo, a compound so structurally stable that fabric dyed with it thousands of years ago can still sometimes show traces of that color today. The active ingredient in opium that makes it so effective at relieving pain is morphine, a complex alkaloid molecule that fits, with almost eerie precision, into receptor proteins in the human nervous system. It fits so well because human brains actually make their own versions of similar molecules. Compounds called endorphins, from the words endogenous morphine, our body's own internal painkillers, released during exercise, laughter, and moments of joy. Isn't that extraordinary? The human brain makes its own version of opium. The poppy plant, through millions of years of evolution, independently arrived at a similar molecular solution. The same basic molecular architecture, created by two completely different biological systems, for, as far as we can tell, completely different purposes. That is organic chemistry. That is the secret language of life. And the people in this ancient marketplace, buying and selling these substances, using them to season their food and dye their cloth and ease their pain and commune with their gods, they are all, without knowing it, participants in a story about molecules. They are actors in a chemical drama they cannot yet see. But some of them are beginning to sense it. Some of them are beginning to ask questions. In ancient India, the practitioners of Ayurvedic medicine are carefully cataloguing the effects of hundreds of plant substances. They are noticing which plants ease fever and which plants ease pain. Which plants are poisonous and which are healing. Which plants, combined together, produce effects that neither plant alone produces. In ancient China, alchemists are experimenting with the transformation of matter, looking for ways to convert base metals into gold, looking for elixirs of immortality, looking for the hidden principles that govern how things change and transform. In ancient Greece, philosophers are arguing about the fundamental nature of matter itself. What is everything made of? What is the basic building block of reality? Democritus proposes that all matter is made of tiny, indivisible particles he calls atomos, from which we get our word atom. Aristotle disagrees and proposes that all matter is made of combinations of four elements, earth, water, air, and fire. Aristotle is wrong. But his wrongness is interesting, because embedded within his wrong framework is a genuine and important insight. That the properties of substances are determined by their composition and arrangement, not by some arbitrary divine will. That matter follows rules. That there is a system here, if only we can find it. And that quest, the quest to find the system, to find the rules that govern how matter behaves and transforms, is the quest that will eventually lead, 2,000 years later, to organic chemistry. But first, it will lead somewhere much darker and much stranger. It will lead to the alchemists. Let us step now into a different kind of room. It is night time. It is always night time in this room, or rather, the night time of this room is always present, even during the day, because the shutters are closed and the only light comes from flames. Candles burning on every available surface. A fire roaring in a great stone hearth, over which hang clay and glass vessels of various sizes, filled with liquids of various colors. Pale yellow, deep green, murky brown, clear as water. The room smells of sulfur and mercury and strange organic compounds being heated and distilled. The person in this room, and there are people like this person scattered across medieval Europe, across the Islamic world, across China and India and Persia, is an alchemist. And the alchemist is trying to do the impossible. Officially, the alchemist is trying to transmute base metals into gold. Officially, the alchemist is trying to create the philosopher's stone, a legendary substance that can not only turn lead into gold but can also, some believe, grant immortality. These are the stated goals, the respectable goals, the goals that might attract a wealthy patron willing to fund years of expensive experimentation. But underneath those official goals, quietly, in the long hours of the night, the alchemist is doing something else. The alchemist is simply, watching. Watching what happens when you heat copper with sulfur. Watching what happens when you dissolve certain minerals in acid. Watching what happens when you distill wine and collect the vaporous, fiery liquid that emerges, the liquid we now call alcohol, derived from the Arabic alcohol, meaning something like, the essence, or, the most subtle part. The alchemists, in their fumbling and symbol-laden and often mystically confused way, were doing chemistry. They were observing chemical reactions, cataloging their results, building up, slowly, imperfectly, but genuinely, a body of empirical knowledge about how substances behave. And some of what they discovered matters enormously to our story tonight. Because many of the substances that alchemists worked with were organic. Alcohol, certainly, ethanol, the compound produced by yeast fermenting sugars, the compound that makes wine wine and beer beer. The alchemists learned to distill it, concentrate it, produce it in purer and purer forms. They called it aqua vitae, the water of life. And in doing so, they were working with one of the simplest organic molecules, a chain of two carbon atoms bearing a hydroxyl group, written in modern notation as C2H5OH. They worked with oils and resins and plant extracts. They worked with vinegar, acetic acid, another simple organic compound. They worked with the materials of tanning and dyeing, all of which involve complex organic chemistry. One alchemist, Jabir ibn Hayyan, known in the Western world as Jeber, who worked in the Islamic Golden Age around the 8th century, is sometimes called the father of early chemistry. He systematically described processes like distillation, crystallization, and sublimation. He emphasized precise observation and careful documentation. He used language that would not be out of place in a modern chemistry laboratory, speaking of the properties of substances and the conditions under which reactions occur. And yet, and this is important, even Jabir did not separate what we now call organic chemistry from what we now call inorganic chemistry. Because that distinction had not yet been made. Because no one had yet noticed the most important pattern hidden within the vast diversity of organic substances. No one had yet noticed that carbon was the key. Carbon, element number 6, sitting quietly in the middle of the periodic table, was everywhere in these organic substances. In the alcohol. In the oils and resins. In the plant medicines and spice compounds and dye molecules. in the bodies of the living organisms that produced all of these things. But the alchemists could not see this yet. Their tools were not precise enough. Their conceptual framework was not yet ready to receive this insight. That would require a revolution. That would require the development of a new way of thinking about matter and chemical reactions. That would require, and here is where our story begins to pick up real speed, begins to develop the momentum of inevitability that all great scientific discoveries seem to have in retrospect, the development of what we now call modern chemistry. And that development begins, as so many revolutions begin, with a man willing to say, everything we think we know is wrong. Paris, 1770s. The city is beautiful and brutal in equal measure. The aristocracy live in extraordinary splendor, powder and silk and candlelit ballrooms, while in the narrow streets below, the poor live in desperate conditions that will, within a few decades, produce one of the most violent revolutions in human history. But right now, in a large and well-equipped private laboratory in Paris, a man is carefully weighing things. His name is Antoine Laurent de Lavoisier, and he is, by any measure, extraordinary. He is wealthy, well-connected, impeccably educated. He has a beautiful and brilliant wife, Marie-Anne Pauls de Lavoisier, who translates scientific papers for him, draws the illustrations for his books, and is, by many accounts, as much his scientific partner as his spouse. And he is obsessed, quietly, methodically, obsessively, with the question of what things are made of and what happens to them when they burn. At the time Lavoisier is working, the dominant theory of combustion, of burning, is the phlogiston theory. According to this theory, all combustible substances contain a mysterious substance called phlogiston, which is released during burning. When something burns, it is releasing its phlogiston into the air. That is why it produces heat and light. That is why it is consumed. The theory is wrong. But it explains a lot of observations well enough that it has been accepted for nearly a century. Lavoisier is suspicious of it. He is suspicious because he notices something that the phlogiston theory cannot explain. When he carefully weighs things before and after burning them in a sealed vessel, the total weight of the system, the substance plus the air, does not change. Matter is neither created nor destroyed. It simply changes form. And that observation, so simple, so obvious in retrospect, so revolutionary in its implications, leads Lavoisier to a completely different understanding of what combustion is. He calls the active component of air that makes combustion possible oxygen. He shows that when things burn, they are not releasing phlogiston, they are combining with oxygen. They are oxidizing. The products of combustion, the ash, the gases produced, contain the oxygen that was in the air. And when Lavoisier turns this understanding toward organic substances, toward burning sugar, burning alcohol, burning fats and oils, he discovers something that will change everything. He discovers that when organic substances burn, the products are always carbon dioxide and water. Always. Every time you burn sugar, carbon dioxide and water. Every time you burn alcohol, carbon dioxide and water. Every time you burn fat, carbon dioxide and water. Lavoisier realizes that this cannot be a coincidence. This pattern, this always getting the same products from such different starting materials, means that all of these organic substances are made from the same basic ingredients. They are all made from carbon, hydrogen, and oxygen, the three elements that, combined in different proportions and arrangements, make up the extraordinary diversity of organic compounds. He cannot yet see how these elements are arranged within the molecules. His tools do not allow him to see the molecular architecture. But he can see the elemental composition, and that is enough to begin the revolution. Lavoisier publishes his work. He writes his famous elementary treatise on chemistry, which introduces the concept of chemical elements as we still understand them today, which presents chemistry as a precise quantitative science of matter and its transformations, which establishes the law of conservation of mass. And in doing so, he plants the seeds of organic chemistry. He also, tragically, plants himself at the center of French political life at the worst possible historical moment. Lavoisier is not just a scientist, he is also a tax collector for the French government, a profession that makes him unpopular with the very people whose revolution is about to remake France. In 1794, at the height of the Reign of Terror, Lavoisier is arrested, tried, and guillotined. The mathematician Joseph-Louis Lagrange, hearing of his death, says, "It took them only an instant to cut off his head, and 100 years may not suffice to produce another like it." And standing at his graveside, or rather, at the unmarked revolutionary grave into which his body was placed without ceremony, we might feel the particular grief of a life cut short, of a brilliant mind extinguished before its time. Lavoisier was in his 50s when he died. What else might he have discovered? We will never know. But what he did discover was enough. The seeds he planted were well rooted. Other scientists would come along to water them. And the question that those scientists would begin asking, a question that would define the next half-century of chemistry, is this: what is the difference between organic and inorganic substances? What makes something alive? What makes something organic? This question would lead to one of the most beautiful and surprising discoveries in the history of chemistry. But to understand it, we need to understand first what people thought the answer was. And what they thought the answer was, at the beginning of the 19th century, is something called vitalism. Settle a little deeper into your comfort now. Because we have arrived at one of the most philosophically interesting moments in our story. It is the early 19th century. Chemistry is becoming, rapidly, a precise and powerful science. Lavoisier's revolution has taken hold. Scientists across Europe are identifying new elements, studying chemical reactions with new precision, building up an increasingly complete picture of the inorganic world, the world of minerals and metals and gases and salts. And at the same time, they are studying organic substances, the substances produced by living organisms. Sugars and fats and proteins and plant compounds and the various products of fermentation and distillation. And they notice something. They notice that organic substances seem to behave differently from inorganic ones. They are often more complex. They are harder to analyze. They seem to have a certain unpredictability. A certain resistance to the simple laws that govern inorganic chemistry. And from this observation grows a belief. A widely held, philosophically attractive, scientifically plausible belief. The belief is this: living organisms are fundamentally different from non-living matter. They are not just more complex arrangements of the same atoms. They contain something extra, a special force, a vital principle, a vis vitalis in the Latin phrase, that animates them, that gives them the properties of life. And the organic compounds that organisms produce are produced through the action of this vital force. This means, and here is the crucial implication, that organic compounds cannot be made by non-living chemistry. They can only be made by living things, through the action of the vital force. You cannot, according to this view, synthesize a sugar molecule in a laboratory using only chemicals and heat and careful technique. Because sugar is a product of life, and life requires the vital force, and the vital force is something that chemistry cannot provide. This belief, vitalism, is not stupid. It is not primitive. It is, in fact, a reasonable response to the evidence available at the time. Organic compounds are genuinely more complex than most inorganic ones. The chemistry of living organisms is genuinely different in many ways from non-biological chemistry. And there is something special about living organisms, something that simple chemistry does not capture. We still do not fully understand the gap between chemistry and biology, the gap between a collection of molecules and a living thing. But vitalism as a specific chemical claim, that organic compounds cannot be synthesized without a vital force, is wrong. And it was proven wrong by one of the most beautiful accidents in the history of science. An accident that happened in a laboratory in Germany in 1828. An accident involving a chemist named Friedrich Wöhler, a kidney stone compound called urea, and a momentous experiment that he described in a letter to a colleague with barely concealed excitement. Friedrich Wöhler is a young chemist working in Germany in the 1820s. He is not yet famous. He is not yet the man whose name will appear in every textbook of chemistry as the person who overturned one of the most fundamental assumptions of his era. He is just a careful, methodical, curious young scientist, working in his laboratory, doing the kind of quiet, unglamorous work that most science actually consists of. He is studying inorganic compounds of nitrogen, compounds that have nothing to do, in his mind, with the organic world. He is specifically working with ammonium cyanate, a simple inorganic salt, made from ammonium ions and cyanate ions, with nothing remotely biological about it. He heats it. He watches it transform. He collects the product. And then he stares at what he has made with growing confusion, because what he has made does not match what he expected. The crystals forming in his dish do not have the properties of ammonium cyanate. They have the properties of something else entirely. They have the properties of urea. Urea. The compound found in urine. The organic waste product excreted by the kidneys of mammals after they metabolize proteins. A compound that is, unambiguously, a product of living organisms. A compound that, according to vitalism, should be impossible to make without the vital force. Wöhler has made it from inorganic starting materials, using only heat. He checks his results. He checks them again. He analyzes the compound he has made with every technique available to him, and every result confirms the same thing. He has made urea. Genuine urea. Chemically identical to the urea in urine. From ammonium cyanate. From an inorganic salt. Without any living organisms. Without any vital force. He writes to his friend and mentor, the great Swedish chemist Jöns Jacob Berzelius, in a letter that is one of the most charming pieces of scientific correspondence ever written. He says, and I am paraphrasing from the spirit of his delighted disbelief, I must tell you that I can make urea without any kidney, and without any animal at all. That sentence. That simple, astonished sentence. It reverberates down through history as one of the great turning points. Because what Wöhler had done, this unassuming young chemist in his German laboratory, not trying to overturn vitalism but simply trying to characterize an inorganic compound, was to demonstrate that the boundary between the living and the non-living, between the organic and the inorganic, was not where anyone had thought it was. Organic compounds. Even organic compounds produced by living organisms as metabolic products, were not fundamentally different from inorganic ones. They were not protected by any vital force or special biological principle. They could be made by chemistry alone. The implications were enormous. Almost vertiginous. If urea could be made from inorganic starting materials, what else could? What were the limits of what chemistry could produce? The answer, which would take the rest of the 19th century and much of the 20th to fully develop, is, almost nothing. Almost anything that a living organism can make, chemistry can also make, given enough time, enough cleverness, and enough understanding of the molecular structure of the target compound. But the story of how chemists developed that understanding, how they went from being able to make urea to being able to make antibiotics and plastics and drugs and flavors and dyes, is a long and wonderful one. And to tell it properly, we need to spend a little time understanding the central concept that makes all of organic chemistry possible. We need to talk about carbon. We need to understand why carbon is different from every other element. Why carbon, and only carbon, is the basis of life. Why carbon is, in the deepest sense, the reason that organic chemistry exists as a discipline separate from all of chemistry. Let us take a moment now to simply appreciate an element. That sounds like an abstract thing to do. Elements are not, in most people's daily experience, things that inspire appreciation or wonder. They are things on a chart. They are things in textbooks. They are things that perhaps you memorized, or tried to memorize, in school. But carbon is different. Carbon deserves your wonder. Carbon deserves your reverence, in the way that anything that is essential to your very existence deserves reverence. Because carbon is in you right now. As you sit or lie here in the quiet of your evening, carbon is the backbone of every molecule in your body. The proteins that give your cell structure, carbon. The DNA that carries the genetic instructions that make you you, carbon. The fats that store your energy and make up the membranes of your cells. Carbon. The sugar molecules that power your metabolism and feed your brain and keep your heart beating, carbon. If you could somehow remove every carbon atom from your body, what would be left would be water and some dissolved salts. Almost nothing. You are, in a very real and literal sense, a carbon-based life form. You are, in the language of astronomy and science fiction, made of stardust. Because the carbon in your body was forged in the hearts of ancient stars long before our solar system existed. But carbon is not special merely because it is abundant in life. Many elements are abundant in living things. Oxygen, hydrogen, nitrogen, these are all present in large quantities in biological molecules. Carbon is special because of what it does. Because of its unique chemical behavior. Specifically, carbon is special because of its valence. The number of chemical bonds it can form with other atoms. Carbon has 4 valence electrons. This means it can form exactly 4 covalent bonds. It can bond to 4 other atoms simultaneously. Now, why does this matter? What does it mean to form 4 bonds? It means flexibility. It means the possibility of constructing molecular structures of almost unlimited complexity. Think about it this way. If you can only form 1 bond, like hydrogen, you are limited to simple, end-of-chain positions. You can stick onto something, but you cannot form the backbone of a long chain or a ring. If you can form 2 bonds, like oxygen, you can link 2 things together, creating simple chains and bridges. But you are still quite limited in the complexity of structures you can build. But carbon, with 4 bonds available, can do something extraordinary. It can link to other carbon atoms. And each of those carbon atoms can link to other carbon atoms. And each of those can link to still others, creating chains that extend for hundreds or thousands of atoms. Chains that can branch. Chains that can loop back on themselves to form rings. Rings that can fuse together into complex polycyclic structures. And at every point along these chains and rings, the carbon atom still has some of its bonds available to link to other kinds of atoms. To hydrogen, to oxygen, to nitrogen, to sulfur, to phosphorus, creating the enormous chemical diversity of organic compounds. This is not a property shared by any other element. Silicon, which sits directly below carbon in the periodic table and has the same valence of 4, is sometimes proposed as an alternative basis for life. And indeed, silicon can form chains. Silicon can link to other silicon atoms. But silicon-silicon bonds are weaker and less stable than carbon-carbon bonds, and silicon cannot form the equivalent of carbon's double bonds or aromatic rings with anywhere near the same ease. Silicon is a pale imitation. A capable element but not a brilliant one. Carbon is brilliant. Carbon, with its 4 bonds and its moderate size and its ability to form both single and double and triple bonds with other carbon atoms and with other elements, creates a chemical space of almost incomprehensible richness. It is estimated that the number of possible organic molecules, the number of different structures you could theoretically build from carbon and hydrogen and oxygen and nitrogen, exceeds 10 to the 60th power. That is a number so large that writing it out would take more space than this entire script. It is, for all practical purposes, infinite. From that effectively infinite space of possible molecules, life has selected a few thousand to use consistently. The sugars, the amino acids, the lipids, the nucleotides, the molecules of life. But chemistry, unfettered by the practical constraints of biology, has access to all of them. And chemists, in the century and a half since Wohler made his urea, have been exploring that vast chemical space with growing confidence and sophistication, discovering new molecules, new reactions, new materials, new drugs, new flavors, new colors, new substances of every kind. All built on carbon. All built on the remarkable, patient, essential element that is also, right now, the backbone of every molecule in your body. Take a breath. Feel that? That is oxygen entering your lungs and binding to hemoglobin, a protein whose structure is built on carbon. Feel your exhale. That is carbon dioxide leaving, a carbon atom you consumed in food, metabolized in your cells, oxidized and exhaled back into the world. You are breathing organic chemistry. You are living it. You are made of it. And now that we understand carbon, now that we feel why carbon is the key, we can begin to understand the structure of organic molecules themselves. We can begin to understand the language that all of this chemistry is written in. We can begin to understand the alphabet of life. In the middle of the 19th century, after Wohler's revelation had opened the door and after a generation of chemists had begun to walk through it, making new organic compounds and studying old ones with new rigor, a problem became increasingly pressing. The problem was, how do we talk about all of this? There are so many organic compounds. Thousands of them. Hundreds of thousands. And the number being discovered, and synthesized, was growing every year. How could chemists communicate with each other about what they were making and studying? How could they predict the behavior of compounds they had never made? How could they build up a systematic understanding of organic chemistry rather than just an endless list of individual facts about individual compounds? The answer would require the development of an entire language. A language of molecular structure. A language built on the concept of functional groups. Recognizable clusters of atoms that appear again and again across different organic molecules and that confer similar chemical properties wherever they appear. Think of functional groups as the letters of the alphabet of organic chemistry. Just as the same 26 letters recombine in different arrangements to make the entire English language, all its words, all its sentences, all its books and poems and love letters and scientific papers. The same handful of functional groups recombine in different arrangements on carbon skeletons to create the entire language of organic compounds. Let me introduce you to some of these letters. Let us begin with the most familiar. The first letter, the most humble, the simplest, is the hydroxyl group. It is just an oxygen atom bonded to a hydrogen atom, hanging off a carbon skeleton like a small flag, OH. And wherever this OH group appears on a molecule, it confers certain characteristic properties. Compounds with OH groups can form hydrogen bonds with water, which makes them more soluble. They have characteristic reactivity. They can be identified by certain chemical tests. The OH group, attached to a carbon chain, makes alcohols. Ethanol, the alcohol in wine and beer, is a two-carbon chain with a hydroxyl group. Glycerol, the backbone of fats, has 3 carbon atoms each bearing a hydroxyl group. Sugar molecules, glucose, fructose, sucrose, have multiple hydroxyl groups adorning their carbon skeletons. The second letter, perhaps the most consequential, is the carbonyl group. This is a carbon atom doubly bonded to an oxygen atom, C=O. And this group, depending on where it sits in a molecule, creates an entire taxonomy of important compounds. If the carbonyl carbon sits at the end of a chain, with a hydrogen atom also attached, it makes an aldehyde. The smell of fresh almonds comes from benzaldehyde, an aromatic ring with a terminal aldehyde group. The smell of cinnamon comes from cinnamaldehyde, a longer molecule with a carbonyl at the end. Even the compound that gives vanilla its characteristic smell and flavor, vanillin, contains an aldehyde group. If the carbonyl carbon sits in the middle of a chain, bonded to carbon atoms on both sides, it makes a ketone. Acetone, the solvent used in nail polish remover, is the simplest ketone, just a 3-carbon chain with the carbonyl in the middle. The sweet, slightly fruity smell of acetone is unmistakably ketone. Your body makes acetone when it breaks down fats for energy during prolonged fasting or in ketosis. Which is why people on ketogenic diets sometimes have breath that smells slightly of nail polish remover. If the carbonyl group sits next to an OH group, if we have C equals O, OH, which is written as COOH, we get a carboxyl group, and compounds with carboxyl groups are carboxylic acids. These are everywhere. Acetic acid, the acid in vinegar, is the simplest, 2 carbons and a carboxyl group. Citric acid, the sharp sourness in lemons and oranges, has 3 carboxyl groups on a 6-carbon backbone. Fatty acids, the building blocks of fats, are long carbon chains ending in a carboxyl group. And if we combine a carboxyl group with an amine group, which I will come to in a moment, we get what is perhaps the most biologically important functional group combination of all, the amide group, the linkage that holds amino acids together into proteins. Let me pause here and let that sink in, because I want you to feel the weight of this alphabet that we are learning. Every protein in your body, every enzyme, every structural protein, every antibody, every receptor molecule, every motor protein that makes your muscles contract, is a long chain of amino acids linked together by amide bonds. The language of every protein is written using these bonds. Hemoglobin, which carries oxygen in your blood. Collagen, which gives your skin its elasticity. Actin and myosin, which power every movement you have ever made. All of them are chains of amino acids linked by amide bonds. And an amide bond is nothing more, imagine the audacity of this simplicity, than a carbonyl carbon bonded to a nitrogen atom. C equals O, N. That is the bond of life. That is the chemical linkage that makes proteins possible and therefore makes you possible. Now let me introduce the amine group, NH2. A nitrogen atom with 2 hydrogen atoms attached. This group appears in amino acids, in the DNA bases that carry genetic information, in neurotransmitters like serotonin and dopamine, in thousands of other biologically important compounds. Amines are often basic in chemical terms, they can accept a proton, and this reactivity makes them essential participants in countless biochemical reactions. And the phosphate group, a phosphorus atom surrounded by oxygen atoms, written PO4 superscript 2. Which holds together the backbone of DNA and RNA, which stores and releases energy in the form of ATP, which participates in cellular signaling cascades of extraordinary complexity. Phosphate groups connect the sugars in your DNA strand, creating the double helix, the spiral staircase of genetic information. And aromatic rings, 6-carbon rings with alternating single and double bonds, beautifully stable structures that appear in benzene and in countless biological molecules. Aromatic rings appear in the amino acids phenylalanine, tyrosine, and tryptophan. They appear in the DNA bases. They appear in hormones like estrogen and testosterone, in vitamins like vitamin K, in the heme group that gives blood its red color. These are the letters. These are the functional groups. And when you learn them, when you can recognize them and understand what they do, you suddenly find that you can read the language of organic chemistry. You can look at a molecule you have never seen before and make reasonable predictions about how it will behave, what it will smell like, whether it will dissolve in water, how reactive it is. You can read the secret language of life. But there is still a piece missing. Because we have talked about functional groups, and we have talked about carbon chains, but we have not yet talked about how those chains are arranged. And the arrangement. The three-dimensional shape of an organic molecule turns out to be as important as its composition. This is the concept of molecular structure, and the story of how chemists came to understand it is one of the most dramatic detective stories in the history of science. Imagine the frustration. You are a chemist in the 1840s or 1850s. You have an organic compound in front of you, a white crystalline solid, say, with a characteristic smell and particular solubility properties. You analyze it carefully and determine its elemental composition. It contains carbon, hydrogen, and oxygen in the ratio, let us say, 6:12:6. 1 carbon for every 2 hydrogens for every 1 oxygen. But this composition, this ratio of elements, describes not one compound but dozens of different compounds with completely different properties. Glucose, which is a sugar. Fructose, which is also a sugar, slightly sweeter, present in fruit. Galactose, which is found in milk. And various other compounds with the same formula but wildly different properties. How can they all have the same elements in the same proportions but behave so differently? The answer, which seems obvious to us now but which required decades of brilliant work to establish, is that they have the same atoms but arranged differently. They have the same letters but spelled differently. They are isomers. The concept of isomerism. The existence of different compounds with the same molecular formula, is both one of the most beautiful and one of the most challenging concepts in organic chemistry. Beautiful because it reveals the richness of molecular space, the fact that the same atoms can combine in multiple different ways to create multiple different compounds. Challenging because it means that knowing the elemental composition of a compound is not enough. You also need to know the structure. The exact arrangement of every atom. And determining the structure of an organic compound, figuring out not just what atoms are present but how they are connected, is enormously difficult without modern analytical tools. The chemists of the mid-19th century had to do it essentially by logic. By chemical reasoning. By a kind of molecular detective work that required both extraordinary experimental skill and extraordinary creative imagination. The key figure in the development of structural organic chemistry is a German chemist named August Kekule. And his story is one of the most famous, and most debated, in all of science. Kekule was working in the 1850s and 1860s to understand the structures of organic compounds. He was one of the first chemists to articulate clearly the idea that carbon forms 4 bonds, the tetravalence of carbon, and that carbon atoms can chain together to form the backbone of organic molecules. His work on the valence theory of organic structure laid the foundation for the structural chemistry that followed. But his most famous contribution, the contribution that has been told and retold in chemistry classrooms and popular science books for over a century, is his proposed structure for benzene. Benzene, with the formula C6H6, was one of the most mysterious compounds in organic chemistry. It was known to be highly stable. It was known to participate in chemical reactions in unusual ways, resisting the reactions that typical carbon-carbon double bonds undergo. Its structure was a puzzle that the best chemists of the era could not solve. And then Kekule had a dream. Or at least, this is what he later claimed. In a famous speech delivered in 1890, Kekule described how the structure of benzene had come to him in a half-waking dream or reverie. He saw atoms dancing before him in chains and spirals, and then one of the chains twisted around and bit its own tail, like the ancient symbol of the Ouroboros, the serpent eating itself. And he woke with the insight, benzene is a ring. A closed ring of 6 carbon atoms. The story of the dream has been discussed and disputed by historians of science ever since. Did it really happen? Was it embellished in the telling? Does it matter? What matters is the idea itself, and the idea was brilliant and correct. Benzene is a ring of 6 carbon atoms, each bearing 1 hydrogen atom, with alternating single and double bonds between the carbon atoms, or, more accurately, with the double bonds delocalized across the entire ring, creating a kind of electron cloud that hovers above and below the ring and gives benzene its characteristic stability. This structure, the benzene ring, also called the aromatic ring, is one of the most important structural motifs in all of organic chemistry. It appears in thousands of biologically important compounds, in many drugs, in many industrial chemicals, in many flavors and fragrances. It is, in a sense, one of the most important molecular shapes ever discovered. And it came, by Kekule's account, from a dream. There is something beautiful about this, something that feels appropriate. Chemistry is, at its best, not just a technical exercise but an act of imagination. The molecules we study are invisible to us. We cannot see them directly. We can only infer their shapes from their behavior, from the results of experiments, from the patterns of their reactions. To understand a molecule's structure, you have to be able to visualize something you cannot see. You have to imagine a molecular architecture that matches all the experimental evidence. This requires imagination as much as it requires analytical skill. And dreams, the mind's own laboratory, where the rules of ordinary logic are relaxed and unexpected connections can be made, are, perhaps, not such an unlikely source of chemical insight. But not all of the great structural discoveries of this era came from dreams. Most came from painstaking experimental work and logical reasoning. And as the century progressed, the tools for determining molecular structure became increasingly powerful. With the structure of organic molecules becoming clearer, with the logic of functional groups and carbon chains being established, the 19th century chemists did something remarkable. They began to build. Not just to analyze existing organic compounds. Not just to study the molecules that nature had produced through millions of years of evolution. They began to synthesize. To create new organic molecules from simpler starting materials. To explore the vast chemical space that the logic of organic structure implied. And in doing so, they accidentally, or sometimes deliberately, created new substances that would transform human civilization. Let us tell the story of a few of them. The first story, one of the most extraordinary accidents in the history of chemistry, begins in 1856 with an 18-year-old chemistry student in London. His name is William Henry Perkin. He is young, idealistic, and working in his home laboratory during the Easter holiday on a project assigned by his professor, the attempt to synthesize quinine, the anti-malarial drug, from coal tar. Coal tar, at this time, is a waste product of the growing gas lighting industry. Gas lights are everywhere in Victorian London, burning coal tar gas to produce the warm glow that lines the streets at night. And the heavy, dark, viscous tar left over from this process is mostly a nuisance, a waste product that has to be disposed of somehow. But chemists know that coal tar contains a complex mixture of organic compounds. And Perkin, following his professor's suggestion, is trying to extract or synthesize useful compounds from it. He does not succeed in making quinine. His experiment fails. But when he adds alcohol to the dark residue left in his flask after the failed reaction, he notices something. A beautiful, rich, vivid purple color. Not the dull reddish-brown or yellowish tinge that he might expect from reaction residues. A genuine, saturated, deep purple, a color that catches the light in a way that makes him look twice. Perkin, resourceful and curious, decides to investigate. He tests this purple substance as a dye on fabric. It works brilliantly. The color is fast, it does not wash out. It is vibrant and attractive in a way that no existing synthetic dye can match. He has discovered what will become known as mauveine, or simply mauve. The world's first synthetic dye. The significance of this is hard to fully appreciate from our modern vantage point, surrounded as we are by fabric in any color imaginable, dyed cheaply and easily and in infinite variety. But in 1856, dyes were expensive and difficult to produce. The beautiful colors that adorned the clothing of the wealthy came from natural sources, from plant extracts and insect pigments and mineral compounds that required elaborate extraction and processing. Purple was perhaps the most expensive and prestigious of all, the famous Tyrian purple of antiquity, extracted from sea snails at enormous effort and expense, was the color of royalty precisely because only the very wealthy could afford it. Perkin had just made purple from coal tar. From a waste product. By accident. At 18 years old. He recognized immediately that this was commercially significant. He patented his process, opened a factory, and became a successful and wealthy manufacturer of synthetic dyes, all before his 21st birthday. And his success inspired others. Chemists across Europe, particularly in Germany, where the chemical industry was rapidly developing into the powerhouse it would become, threw themselves into the study of synthetic dyes. New colors were discovered. The structures of natural dye compounds were determined and then improved upon. An entire synthetic dye industry sprang into existence within a decade or two of Perkin's discovery. And in the process, chemists learned an enormous amount about organic chemistry. The synthesis of dyes required understanding the structures of aromatic compounds, the reactions of functional groups, the conditions under which specific transformations could be carried out reliably. The dye industry was, in a sense, the first large-scale laboratory in which the principles of organic synthesis were worked out. And it led directly to something even more consequential. Because the same chemists who were synthesizing dyes began to notice that some of their compounds had interesting biological effects. Some were antimicrobial. Some affected the nervous system. Some killed specific bacteria or parasites. They began to wonder, could the same approach, the rational synthesis of organic compounds from coal tar and other cheap starting materials, be applied to medicine? Could they design and make drugs? The dream of making medicines from chemistry. Of designing specific molecules to treat specific diseases, is one of the most ambitious and consequential dreams in human history. Before the late 19th century, medicine was almost entirely empirical. Doctors and healers used substances that they knew from experience had certain effects: willow bark to reduce fever, which we now know contains salicylates, precursors of aspirin; foxglove to treat heart failure, which contains digitalis glycosides; opium to relieve pain, containing morphine. But they could not explain why these substances worked. They could not improve upon them. They could not design new medicines from first principles. The German bacteriologist Paul Ehrlich changed this. Ehrlich is one of the most important figures in the history of medicine and chemistry, and his intellectual journey is one of the most instructive. Ehrlich began by studying how dyes interacted with biological tissues. He noticed that different dyes stained different types of cells selectively. Certain dyes would bind to bacteria but not to human cells, others would bind to specific types of human tissue but not others. This selective binding fascinated him. He began to think about it in terms of molecular compatibility. The dye molecule fits the bacterial cell in a specific way, the way a key fits a lock. Because of some chemical complementarity between the structure of the dye and some structure in the bact. Take a moment right now, wherever you are, and look around at the objects within your reach. The device you might be using to listen to or read this, it has a plastic casing. The furniture around you, likely some plastic components. Your clothing may contain synthetic fibers. The bottle you might have nearby for water, almost certainly plastic. We live in the age of polymers. We are surrounded, daily, hourly, constantly, by synthetic organic materials that did not exist 150 years ago. Materials that were created by chemists who learned to harness the power of carbon chemistry to build new kinds of molecules, molecules longer and more complex and more controllable than anything that nature had previously produced. The word polymer comes from the Greek, poly meaning many, mer meaning part. A polymer is a molecule made of many repeating units, linked together in a long chain. Think of it like a necklace made of beads, where all the beads are the same. Each bead is a monomer, a single unit. The necklace is the polymer, the long chain of repeating units. Nature, of course, has always made polymers. The cellulose in wood and cotton, that is a polymer of glucose. The proteins in your body, polymers of amino acids. DNA, a polymer of nucleotides. Rubber, made from the rubber tree, a polymer of isoprene. Nature is, in a sense, a master polymer chemist. But the synthetic polymer revolution began in earnest in the late 19th and early 20th centuries, and it began with an attempt to replace something natural with something artificial. The first synthetic polymer of major commercial importance was bakelite, invented in 1907 by the Belgian-American chemist Leo Baekeland. Baekeland was looking for a synthetic substitute for shellac, a natural resin secreted by the lac bug, used as an insulating material in the rapidly growing electrical industry. He mixed phenol and formaldehyde, both simple organic compounds, under heat and pressure, and produced a hard, dark, heat-resistant solid that could be molded into almost any shape and would retain that shape forever. It was called bakelite, and it was the first truly synthetic plastic. It seemed miraculous. Here was a material that had never existed anywhere in nature, that had been created entirely by human chemistry, that was harder and more heat-resistant than most natural materials, and that could be produced in any quantity from cheap chemical starting materials. Bakelite appears in early radios and telephones. In jewelry and billiard balls. In electrical insulators and kitchenware. It transforms manufacturing, making possible the mass production of complex molded parts that previously would have required expensive machining from wood or metal. And Bakelite was just the beginning. The 20th century saw an explosion of synthetic polymers, a creative efflorescence of new materials, each with unique properties, each opening new possibilities. Nylon, invented by Wallace Carothers at DuPont in 1935, was the first synthetic fiber. A polyamide with chains of repeating units linked by amide bonds, those same amide bonds, remember, that link amino acids in proteins, nature had found this chemistry first. Nylon stockings, introduced to a breathless American public in 1940, sold out immediately wherever they were available. Nylon replaced silk in women's stockings, a wartime sacrifice when silk was diverted to parachutes became easier to bear when nylon was available. Polyethylene. The ubiquitous plastic of bags and bottles and countless other applications, was discovered accidentally twice. Once in the early 1930s at ICA in Britain, when a high-pressure experiment on ethylene gas produced a waxy, white solid. And again, more reproducibly, in the late 1930s, when the conditions for its controlled synthesis were worked out. Polyethylene is the simplest possible polymer, just a chain of carbon atoms, 2 hydrogens per carbon, extending for thousands of units. Nothing simpler could be imagined. Yet this nothing simpler molecule became perhaps the most produced synthetic material in human history. Teflon, polytetrafluoroethylene, in which the hydrogen atoms of polyethylene are replaced by fluorine atoms, was discovered accidentally by Roy Plunkett at DuPont in 1938, when a cylinder of tetrafluoroethylene gas he was about to use for an experiment was found to contain a waxy solid instead of gas. The material was extraordinarily unreactive. The carbon-fluorine bond is the strongest single bond in organic chemistry, making it the perfect non-stick coating. Polystyrene. Polyvinyl chloride. Polypropylene. Polyester. Polyurethane. Polymethyl methacrylate, the clear plastic known commercially as plexiglass or lucite. The list goes on, a roll call of materials so familiar that we have forgotten how recently they entered our lives, how strange and wonderful they must have seemed to the people who first encountered them. And underneath all of this diversity, all of this material richness, is the same fundamental chemistry, carbon atoms linking together in long chains, functional groups providing reactivity and diversity, the structural principles of organic chemistry applied on a grand manufacturing scale. But while polymers were transforming the material world, another branch of organic chemistry was beginning to unlock some of the deepest secrets of life itself. Because chemists were turning their attention to the molecules that carry out the work of living organisms. To proteins and sugars and fats and, eventually, to DNA. And what they found there was more extraordinary than anything that any science fiction writer of the time had imagined. Let us sit for a moment in the quiet complexity of your own body. Right now, as you breathe and blink and perhaps shift slightly to find a more comfortable position, thousands of different proteins are at work inside you. Some of them are structural, they form the scaffolding of your cells, the cables of your muscles, the framework of your skin and hair and nails. Some of them are catalytic, they are enzymes, molecular machines that accelerate the chemical reactions of life to speeds that would otherwise be impossibly slow. Some are motors. Proteins that literally walk along tracks inside your cells, carrying cargo from one place to another, using the energy of ATP hydrolysis to take mechanical steps in a directed direction. The discovery that molecular machines exist, that evolution has built genuine machines at the nanoscale, made of proteins, performing mechanical work, is one of the most astonishing findings of 20th century biology. Some proteins are receptors. Stationed on the surfaces of cells, waiting for specific signal molecules, changing their shape when the right molecule arrives and triggering cascades of events inside the cell. Like tiny locks waiting for their specific keys. Some proteins are channels, tunnels through the membranes of cells, allowing specific ions or molecules to pass in and out, controlling the chemistry of the cell's interior with remarkable precision. All of these proteins, all of this extraordinary diversity of function, are built from the same basic vocabulary, 20 amino acids, linked together in different sequences, folding into different three-dimensional shapes. 20 amino acids. 20 letters. And from those 20 letters, life writes a proteome of hundreds of thousands of different proteins, each one uniquely suited to its particular function. The amino acids themselves are small organic molecules. Simple enough that many of them can be synthesized easily in a laboratory. They all share a common structural core, a central carbon atom bearing an amino group, NH2, a carboxyl group, COOH, a hydrogen atom, and a variable side chain that differs from amino acid to amino acid. It is this variable side chain, called the R group, that gives each amino acid its unique chemical character. Glycine, the simplest amino acid, has just a hydrogen atom as its R group. Alanine has a methyl group, just one extra carbon atom with 3 hydrogens. Serine has a hydroxyl group on its side chain, making it capable of hydrogen bonding. Cysteine has a sulfur-containing side chain that can form disulfide bridges, special covalent bonds that help hold protein structures together. Phenylalanine, tyrosine, and tryptophan have aromatic ring side chains that make them relatively nonpolar and water-avoiding. Each of these side chains has specific chemical properties. Specific tendencies to attract or repel water, to form hydrogen bonds, to participate in certain types of reactions. And these properties determine how the protein folds. Because here is the extraordinary thing about proteins, the sequence of amino acids in a protein, the primary structure, determines, through the physical chemistry of atomic interactions, the three-dimensional shape that the protein will adopt. The protein folds spontaneously into its functional shape, driven by the same physical forces that govern all molecular behavior, hydrogen bonding, hydrophobic interactions, electrostatic attractions, and the entropy of the surrounding water. Understanding this, understanding how the sequence of a protein determines its structure, and how its structure determines its function, is one of the great scientific projects of the 20th and 21st centuries. It is enormously complex. Proteins are not simple objects. A typical protein has hundreds or thousands of amino acids, and predicting how such a chain will fold into its functional three-dimensional structure requires understanding an almost incomprehensible number of molecular interactions. For decades, the protein folding problem was one of the great unsolved problems of science. Chemists and biologists and physicists and computer scientists all worked on it, developing increasingly sophisticated computational models, using X-ray crystallography and nuclear magnetic resonance spectroscopy and electron microscopy to determine protein structures experimentally. And then, in 2020, something remarkable happened. A company called DeepMind, using a deep learning system called AlphaFold, essentially solved the protein folding problem computationally. AlphaFold could predict the three-dimensional structure of a protein from its amino acid sequence with accuracy comparable to experimental determination, a feat that had seemed decades away just a few years before. The implications of this achievement, still being worked out, are immense for medicine, for biotechnology, for our understanding of life. Because understanding protein structure means understanding how proteins function, how they can be modified, how new proteins can be designed for new purposes. But proteins, extraordinary as they are only one of the 4 major classes of biological molecules. Let us briefly visit the others. Lipids, fats and oils and related compounds, are the molecules that make up the membranes of cells, that store energy in long-term reserves, that serve as signaling molecules and hormones. Lipids are predominantly built from fatty acids, long hydrocarbon chains, carbon atoms linked in chains of 8 to 24 atoms, with varying degrees of unsaturation, double bonds between carbon atoms. Saturated fatty acids have no double bonds, every carbon-carbon bond in the chain is single, and the chain is straight and relatively rigid. Unsaturated fatty acids have one or more double bonds. And each double bond introduces a kink into the chain, making the molecule less rigid and more fluid. This is why animal fats, which are rich in saturated fatty acids, are solid at room temperature, while vegetable oils, which are rich in unsaturated fatty acids, are liquid. The membranes of your cells are made of a specific class of lipids called phospholipids, molecules with a polar, water-loving head group, containing a phosphate, and two non-polar, water-avoiding fatty acid tails. These molecules spontaneously arrange themselves into a double layer, a bilayer, with the heads facing outward toward the water on either side and the tails facing inward, away from water. This structure, the lipid bilayer, is the universal membrane of all living cells. It separates the inside of the cell from the outside world, creating the controlled chemical environment in which life's chemistry can occur. Carbohydrates, sugars and their polymers are the molecules of energy storage and structural support. Glucose, the simple sugar that serves as the primary fuel for most cells, is a 6-carbon ring with multiple hydroxyl groups. Sucrose, table sugar, is a disaccharide, 2 simple sugars linked together. Starch and glycogen, the storage forms of sugar in plants and animals respectively, are polymers of glucose, long chains of sugar units linked together that can be quickly broken down to release glucose when energy is needed. Cellulose, the structural material of plant cell walls, is also a polymer of glucose, but linked in a slightly different way that makes it rigid and indigestible by most animals. Termites, with their specialized gut bacteria, are the notable exceptions. And then, the most famous, the most consequential, the molecule that changed everything we know about life and heredity and the relationship between chemistry and biology, DNA. Deoxyribonucleic acid. The molecule of heredity. The molecule in which the instructions for building every living organism on Earth are written.